today's meeting. All right, today we are talking about a concept called DeMorgan's laws. So, to recap our discussion of logical operators from last time, if I have two Booleans, let's say I have Boolean is rainy and is too hot, and my nice day is going to equal not is rainy and not is too hot. And then if it's a nice day, if nice day is true, we'll print what a nice day. Otherwise, we'll print better stay inside. So, is rainy and is too hot, both of those are false. So what is not false and not false going to equal? True. Not false and not false, both of those are going to equal true. True and true is going to equal true. Therefore, we will print what a nice day. It is not rainy, it is not too hot, it is a nice day. So we can actually rewrite this Boolean expression from not is rainy and not is too hot. We can rewrite that as not is rainy or is too hot. So what we're doing is we're kind of pulling the not out of both, and we're swapping the and to an or. So the rule that lets us do this is that's one of DeMorgan's laws. Augustus DeMorgan, pictured on the left here, realized that certain Boolean expressions, certain Boolean statements are equivalent to one another, and he made these rules that we can use to evaluate those the exact same compound Boolean expressions. So we have two laws, and they're when we try to use a not with an and or an or. So if I say not A and B, that is equivalent to not A or not B. So we are going to distribute the not across both, and we're going to swap our operator. Same with our and. Not A or B is going to swap to not A and not B. We distribute the not, and we flip the operator. So let's prove that that is true. We're going to use truth tables. We used a little bit of these last class with our logical operators. But truth tables are a tool that we can use to figure out every possible result of a Boolean expression. So first, let's fill in our A and B columns with every possible permutation of A and B. So what are the possible permutations of A and B here? Let's say when A is true, can B be true? Yeah. All right, so when A is true, B can either be true or false. So and then when A is false, B can also, once again, be either true or false. So that is every possible combination of the values for A and B. There's no state in which we're not going to fit into one of those two rows or four rows. So I have my actual colors here. So we can fill in our A and B using those two columns. What is true and true? True. True and true is true. True and false is false. Everything else is false. So we can say not of this previous column, and the spacing doesn't work out because reasons I don't understand. So not A and B, we're going to use this column and turn it backwards. So we're just going to flip all of our trues to falses, all our falses to true. So not A and B gives us false, true, true, true. So let's look at making sure that that column we just made make sure that that is equivalent to not A or not B. Using those same two columns for A and B. Not A, we're just going to flip all of our trues to falses, and same with B. So we get false, false, true, true, false, true, false, true. And now we can OR those two columns together. False or false, what's that give us? False. False or true? True. True or false is also true. And then true or true is true as well. So if we look at those columns, they have the same order. We have false, false, true, 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 true. Those two columns are equivalent, which shows us those two Boolean expressions evaluate to the same thing in each of those different scenarios. And we can prove the other one as well. What's A or B going to be? True or true? That's true. True or false? Also true. False or true? Once again, true. False or false is false. If we negate that column, we get false, 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 true. Oh, I just skipped. And then not A and not B, we're going to use those same two columns as before. False and false gives us false. False and true, false. True and false, false. True and true is true. So once again, we have those two columns that we're trying to compare against each other. We can see that those are equivalent to each other when we have the same values of A and B. So those two Boolean expressions are equivalent. This is the way we can prove the equivalence of those expressions. Does that all make sense? Cool. All right, so using DeMorgan's laws, what would be the equivalent of this Boolean expression? Not x greater than 3 and y less than 5.
X greater than 3 or y less than 5.
Very close. You did not distribute the not. So we have not x greater than 3 or not y less than 5. And we can kind of distribute that not ourselves as well. Not x greater than 3 is going to be x less than or equal to 3. And not y less than 5 is going to equal y greater than or equal to 5. So all three of these Boolean expressions are equivalent to one another using DeMorgan's laws. Make sense? Yeah? Cool. All right.